Okay, recall that the definition of convergence is that we say that Sn converges to S, a sequence Sn converges to S, if for every epsilon greater than 0, there exists a natural number n, such that when n is bigger than or equal to capital N, we have that the distance of the Sn from the limiting value S can be made less than epsilon. And if this is true for all epsilon, that means that Sn will converge to S. Now, as we've seen in proofs in sections 4.1 and 4.2, being able to determine or prove that a sequence converges requires knowing what the limit is in advance of performing the problem. So, what happens? What happens if we don't know what the actual limit is? We don't know the limit test. We may run into some circumstances or some situations where either the S is not known beforehand, or it's difficult to figure out, or maybe it's just something that's subtle and we might make an error. So it'd still be useful in some contexts to know whether a sequence converges without actually knowing what the limit is. So to lay some groundwork for that, let's first set up some definitions. A sequence Sn is increasing if Sn is less than or equal to Sn plus 1 for all natural numbers. Notice that it is not strictly increasing. It could be constant. I'm just saying that each term S sub n has to be smaller than the next term, S sub n plus 1. So, conversely, or not conversely, but in another sense, what would it mean to be decreasing? Well, this would occur if Sn was bigger than or equal to Sn plus 1 for all n in natural numbers. For here, we would have the previous term, S sub n, being bigger than or equal to the next term. So in other words, the next term has become smaller than the previous term, smaller than or equal to. So increasing effectively means that the elements of the sequence are non-decreasing. They're going up or they're the same, and decreasing would mean that successive terms of the sequence are either becoming smaller or staying the same. And then we will say that a sequence is monotone if it is either increasing or decreasing. In other words, think of the mono from monotone meaning one. It's going in one direction. It's either going upward or it is going downward. Okay, so here are some examples. Cn equals 2 minus 1 over n. So what would the sequence Cn be? Well, if we replace n with 1, we get 2 minus 1 over 1, which is the number 1. If we replace n with 2, we have 2 minus 1 half, which would be 3 halves. If we replace n with 1, 2, 3, we'd have 2 minus 1 third. So that would be 6 thirds minus 1 third. So we're looking at a 5 thirds here. And if we were to replace with 4, we'd have 2 minus 1 fourth, or 8 fourths minus 1 fourth. So it looks like about a 7 fourths there, 7 fourths, etc. Now, I'm not doing a proof here, but hopefully you can see by the examples of the numbers here that the numbers are getting larger each time. 1, 3 halves, 5 thirds, 7 fourths. They're getting larger and larger and larger, and it is actually also bounded, you might notice, because on the low end, the lowest we get is 1, and since the terms seem to be increasing, we have an increasing sequence, a monotone sequence here increasing, we can see that the numbers are getting larger, but they never seem to get past 2. And that might be kind of obvious from the name or from the definition here, but they never get any larger than 2 because they're always 2 minus something. So this is a monotone increasing sequence. Monotone increasing. And it is also bounded. And it is bounded. Okay, let's look at the second example here. This DN sequence is 1, 2, 2, 3, 3, 3. Can you guess what's coming next? 4, right? It's a sequence that has terms that are always increasing, non-decreasing. Notice sometimes here, unlike the CN sequence, this sequence has terms that are repeating 2, 2, 3, 3, 3, but it never goes 3, 3, 3 and then back to 2. The numbers are either getting larger or they're staying the same. So this is an example of a sequence which would be also monotone, either increasing or decreasing. This one is increasing, and it is unbounded this time. Right? It's unbounded. It keeps getting larger and larger and larger following the pattern. So it doesn't stop at any stage. Okay, as a last example, let's look at this activity. Feel free to pause the video if you wish and write out a few terms of this. But assuming you had a chance to stop the video and see if you could write out a few terms of this, let's look and see what they are. The first term would be if we replaced n with the number 1. 1 minus negative 1 would be 2. The next term would be if we replaced n with the number 2. The second term of the sequence would be negative 1 squared, which is 1, and 1 minus 1 is 0. The third term would be an odd exponent giving us a negative again, so that's going to be 2, and then it's going to be 0, and then 2, and then etc. So we've already run into this sequence in previous lectures. Notice this is not monotone. It is not strictly, or it's not non-decreasing and it's not non-increasing. Notice that the numbers are jumping back and forth. So there's a place where numbers get smaller than they were before, increasing it, or indicating a decreasing nature. But then there's places where the next number becomes larger, indicating an increasing nature. So we don't have any monotonicity here. It's not increasing nor decreasing. This particular case, it is bounded. This particular sequence is bounded. Because notice that it never exceeds 2, and it never gets smaller than 0. Because in fact, the only two outputs we ever get are 0 and 2 from this particular sequence. Okay, the first big theorem is going from this section is Monotone Convergence Theorem. Monotone Convergence Theorem. I might abbreviate this sometimes by MCT. And we say that, or we find that a monotone sequence, remember it's either increasing or decreasing, is convergent if and only if it happens to be bounded. Okay, let's go about trying to prove this. So what would the forward direction be? The forward direction would be, we want to show that a monotone sequence is convergent if a monotone sequence converges, then it is bounded. Okay, we actually did, this was proved earlier in the textbook. I think it might have been section 4.1. But at any rate, the lecture on that day had gone a little bit long, so we didn't get a chance to rigorously show this in class. So since we're making a new video here, why don't we just show this concrete, or actually do the proof. So let's suppose that a sequence Sn converges to a value, call it x. Okay. I actually don't even need monotonicity here. It's enough to know that it is actually just convergent. That's what it was in that first section. But we'll just take the loosest assumption here that it converges. But of course, if it's true for a convergent sequence, it'll also be true for a monotone convergent sequence. So if we have something that is convergent, what do we say? Well, in the definition of convergence, let's let epsilon equal 1. Now, the definition of converging is for all epsilon. So in particular, the definition of convergence will hold for epsilon equal to 1. So what do we get from that? If we let epsilon equal 1, then by the definition of converging, we know that there exists n in n such that We get that n bigger than or equal to capital N will imply that Sn minus S can be made less than any epsilon, in particular, our value of 1. Right? Now, therefore, maybe we should just say therefore. Therefore, we proved earlier on that if we have this condition of Sn minus S being less than 1, that we actually get, for n bigger than or equal to n, the fact that Sn is going to be less than absolute value of S plus 1. Right? In other words, if our distance from the limit of the sequence is less than 1, then that means that for all of these values that are close to it, that if we take the SNs, they're also going to be less than that limiting value plus 1 on the high end. Minus 1 on the low end, but definitely plus 1 on the high end. Okay, so remember by the definition of boundary, we have to find a maximum. So let's let M equal the maximum, or the biggest element. We just need to find an upper bound, and we'll let it be the maximum of, first of all, the terms that we didn't have any kind of connection on, S1, S2, dot, 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 and we'll go all the way out to S capital N, which is given by that N that already exists. And then for all the N's that exceed that capital N, we know that they're going to be less than the absolute value of S plus 1. That was an upper bound on all of the remaining terms. So we have the first capital N many terms from wherever, and then for the infinitely many terms beyond capital N, we have that the absolute value of the limit of the sequence plus 1 would be an upper bound on all of them. So what is true about that thing is that now every value of the sequence, absolute value of any value of the sequence, will be less than or equal to capital M for all n in n. And that's effectively what the proof of the bounded sequence, that a convergent sequence that was bounded, would look like. Okay. So that kind of covers the forward half of the monotone convergence sequence, or monotone convergence theorem. So now we need to go for the backwards direction. Backwards direction would say a monotone sequence, let's back and look at it, if we're going backwards, but that bounded implies convergence. So if a monotone sequence bounded, then it converges. Okay? This is our want to show. This is not the proof, of course. This is the piece that we want to show in order to establish this fact. Okay, so let's think about this for a second. We want to try to show that a bounded sequence converges. So that a bounded sequence converges. So let's just do one case. I'll leave the other case for you to try on your own. Case one, it's monotone. We don't technically know if it's increasing or decreasing. So let's say that, suppose Sn is a bounded increasing sequence. Let S equal the set of the values of the sequence. So in other words, let Sn, the set of Sn, such that n is a natural number. Now notice I'm letting this be a set now. It's not the sequence, not the ordered n tuple or infinite tuple, if you want to call it that. It's just the values of the sequence. Are repeated, we don't need more of them. But since these are the values of the sequence, and we know that the sequence is bounded, we have a bounded set of real numbers right here. So what happens if we have a bounded set of real numbers? Well, by the completeness axiom, a bounded set of upper bound. So we can let little s equal the soup of s. Remember, any set of fields always has a least upper bound. Okay, now we are going to show that not only that we have a sequence that converges, we need to show that this converges. We're going to show that it actually converges to s. That's actually going to be our goal. So we want to show that the limit of the SNs actually goes towards this of the set of the range. So to see this, how do we prove something converges? Same idea for a G cap. Epsilon greater than 0, B given. Epsilon greater than 0 is given. Then that means S, the soup, minus epsilon is not an upper bound for S. Wow. Right? Because was the soup, which is the least of all the upper bounds. So it's not, if we subtract a positive number from that, it's going to be an upper bound. Therefore, there exists some n in n. And remember, the second stage of the definition of convergence is we have to find a capital N that works correctly. Well, we can find a capital N such that what happens? We're going to be able to find a capital N so that S capital N is definitely larger than S minus epsilon. Because S minus epsilon was not an upper bound. So eventually S sub capital N will be larger than S minus epsilon, which is not an upper bound. But since Sn is increasing, since it was monotone, right, and we know that it was increasing by our function, larger than that particular object. So S minus epsilon, which was our not upper bound, is definitely going to be less than S capital N, like we're saying right here, but then that's going to be less than or equal to S sub little n because of the monotonicity, because of the fact that it's always increasing, and because S was a soup, we know that's always going to be less than or equal to n. And this is true for all n. This is true for all natural numbers n. Notice that does exactly what we need here now. So hence, therefore, what? We have Sn converges S. We showed that it's always less than or equal to, so it satisfies the definition of convergence. And that's an MWO on that. Well, technically, we only did it for increasing, so I should put a quote on MWO, and then we'll put a little note to ourselves to verify at home or verify on your own, try to follow the same type of proof and show it for a decreasing sequence. Verify for decreasing sequence. But the proof would be very similar. If we were in class, I would hopefully have a moment here where you could try to do this on your own, 5 or 6 minutes, and try to figure that out on your own. So maybe pause the video, see if you can do this on your own, mimicking this kind of proof, and then you'll see how these arguments kind of hold in general. Okay, so finally an application, right? Here's an application of using the monotone convergence theorem. So let T1 equal 1, and let Tn plus 1 be Tn plus 1 over 4. So what would this sequence look like? Well, first term of the sequence, T1 is 1. In order to get T2, we have to take 1, the previous term, T1, 1 plus 1, which is 2, over 4. So we get the number 1/2. Now we have to take the number 1/2 and add 1 to that, which is 3/2, and then we take 3/2 and divide by 4, so we get 3. eighths. Okay, maybe one more. Let's see, 3 eighths plus 1, which would be plus 8 eighths, would be 11 eighths. Then we divide that by 4, and we're getting 11 over 32. Okay? So notice that these terms right here do appear to be getting smaller, don't they? 1 is less than 1/2, 1 is bigger than 1/2, is bigger than 3/8, is bigger than 11 over 32. These numbers appear to be getting smaller and smaller and smaller, but you really sort of have to show that it's monotone. We can't just say that things look like they're monotone. So let's try to show that the sequence is monotone. And of course, if we're trying to show that something is in general true about all natural numbers, then instinct for this should be to try to do something by induction. So let's try to prove Tn is monotone by induction. Let's approach this by induction. So what would a base case look like? Well, base case would be just to look at the n equals 1 case, right? Can we make sure that we're getting smaller over just one set, or one step? So what exactly is T1? We want to try to show T1 is less than T2. Well, T1 is 1. That's equal to T1. And what is T2? Well, T2 is 1/2. So we do see, indeed, that T1 is bigger than T2. No? That's the base case. So the second term did become smaller than the first term. Okay, no sweat. So now, let's go into an inductive hypothesis. And in the inductive hypothesis, we'll say, suppose that Tk is bigger than Tk plus 1 for some k. Okay? So that's where we are in that stage. Tk plus 1 and then Tk plus 1k. Tk plus 1 for some k. Okay, let's go see what Tk plus 1 is. So, inductive step. Notice Tk1 is equal to what? Well, let's go back up and look at the definition. That's equal to Tk plus 1 over 4. Right? Now, the inductive hypothesis said that Tk was bigger than Tk plus 1. So that means that this would be definitely bigger than Tk plus 1 plus 1 over 4. Because I made the numerator on the fraction smaller due to the inductive hypothesis. But by definition, that's precisely Tk plus 2, right? Replace the n with the k plus 1, and that's just Tk plus 2. So a fairly simple inductive argument tells us that this definitely is a monotone decreasing sequence. By induction, the sequence is monotone decreasing. Nice. We use our theorem yet? No, the monotone convergence sequence said it had to be monotone, which we have, but we also needed it to be bounded if we knew it was going to be convergent. So let's try to show that Tn is bounded. Okay, Tn is bounded. So again, let's look at these numbers. We have 1, 1/2, 3/8, 11 3/2, or 11 32nds. This does appear to be bounded. Doesn't it look like it's bounded? And hopefully it's bounded below. We don't want it to decrease too much. We see that it's decreasing. What do these numbers always look like they're bigger than? Well, I guess I'm always going to be putting a positive number in here, right? Tn will always be a positive number, at least it's a positive number so far. And then I'm adding 1 to it. These numbers are less than 1. And then I'm dividing by 4, so it feels like I'll always be positive. Let's see if we can try to show that. So if I want to show Tn is always positive for all values of n, this again sounds like an induction proof. So let's go by induction again. Base case. T1 equals 1, which is positive. So T1 equals 1 is positive. That's our base case. Inductive hypothesis. Let's suppose that Tk is positive for some k. Okay, then what would our inductive step be? Well, now we have to consider the number tk plus 1. I'm hoping I can show that this is positive. Okay, so what is tk plus 1? Well, tk plus 1 is equal to tk plus 1 over 4, right? Which is equal to k over 4 plus 1/4. tk is positive by the inductive hypothesis. So if we divide that by 4, we're also going to be positive, right? Maybe let's go bigger than or equal to 0 to be safe here. So bigger than or equal to 0, because tk over 4 is definitely going to be bigger than or equal to 0 because tk was bigger than or equal to 0. And then all I'm doing is adding on a positive number to that. So this is certainly going to be bigger than or equal to 0 also. So conclusion, by induction, what do we get? We get that t sub n is bigger than 0 for all n. So yay, MW there. So that means we now have a sequence which is bounded, and in addition to being bounded, it's monotone decreasing. So now we know Tn converges. Tn is definitely going to converge. And the proof of this, think about it for a second. Pause the video. Just do a one-line proof now. And assuming you've had a second to pause the video and just think about it for a second here, the proof here is just by MCT, by the Monotone Convergence Theorem, Tn converges. Very short proof, because remember, in order to be converging, the Monotone Convergence Theorem said what? It said that a monotone sequence is convergent if and only if it is bounded. Monotone sequence is convergent if and only if it is bounded. And here we showed that it is monotone, and here we showed that it was bounded. So we know that it converges. We don't know what it converges to, but we know that it converges. So what is the actual limit? Well, remember by the homework, we knew that by homework 4.1.11, we know that there is a limit, and that it doesn't matter if we ignore the first couple terms, the first few terms. So since we know that there is a limit, let's call that limit t. And then by the fact that we know now that it converges, the limit of the tn's and the limit of the tn plus 1's will be the exact same limit. You proved that one in homework. So that means that limit of tn, the left-hand side here, that would be t, and the limit of the tn plus 1 would be provided by the definition of the sequence. Right? The definition of the sequence, tn plus 1, was tn plus 1 over 4. This would be t plus 1 over 4. Because in limit, the sequence tn plus 1 also converges to t. And this gives us a nice algebraic equation that we can use to solve for t. Notice we needed it to converge before we were allowed to say this, but now that it converges, we can say that this relationship must hold. So what does that mean? Well, this would mean that 4t would be 1t plus 1. Subtract t from both sides, that makes 3t equals 1. And divide by 3, we actually get that t equals 1/3. So that sequence does converge, and it converges to the value of 1/3. Okay, some additional facts that can be shown here are that if Sn is an unbounded increasing sequence, then the limit of Sn's must go towards positive infinity. So, as an example, remember this sequence down here? That sequence was 1, 2, 2, 3, 3, 3. We talked about how it was monotone increasing, but it was unbounded. So what that implies, that little extra factoid, means that this particular sequence is going to go off towards infinity. I should have come back here for a second too. Notice this one up here was monotone increasing and bounded, so this sequence actually does converge by the MCT. It converges to 2, by the way. Now, back to the future. If Sn is unbounded and decreasing, then it must go off to negative infinity. So the limit of the Sn's must be negative infinity. So you have a sequence that keeps on going up, 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 up with no bound. It's going to go to positive infinity, and if it's going down, 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 down without any bound, it has to go down to negative infinity. Okay, so that's one way of showing that a sequence converges, even if you don't know what the limit is necessarily. The second way is called Cauchiness, or the Cauchy criterion. So we say that a sequence Fn is Cauchy if for each epsilon greater than 0, there's a natural number n such that both m and n being bigger than capital N implies that Sn minus Sm is less than epsilon. So recall from previous lecture, sequences tend to look something like this, right? As a very simple example, not only this, but like many different examples. S1, S2, S3, and then maybe an S4, and then maybe an S5. It's starting to get too hard to label them in here, but you can imagine what it would look like. And if something converges to S, that means that our standard definition was that all of the terms get infinitely close to that limiting value of S. But notice that as they get really, really, really close to S, they actually become really, really close to each other also. So that's what Cauchiness is. Cauchiness, notice, does not depend on S. So you can use the Cauchy criterion when you don't actually know what the limiting value S is, as long as you know that the terms are getting infinitesimally close to each other. And that's the idea of Cauchy. So Cauchiness can be thought of as means the terms of the sequence are getting, the terms of the sequence are getting very, very close to not the limit of the sequence, because again, this section is supposed to be about cases in which we don't know what the limit is, but we do know that they're getting very, very close to each other. Because beyond Mn past this capital N, the difference between Sn and Sm is being made less than epsilon. Okay, now, first step. Let's first show that every convergent sequence is Cauchy. We're going to need a couple letters, and then we can move on and actually prove the big Cauchy criterion. That's what I'm going to call C3 here eventually. So every convergent sequence is Cauchy. That's going to be our attempt here. Every convergent sequence is Cauchy. So, how do we start a proof? Pause the video for a second, think about it on your own. We want to show that if something's a convergent sequence, then it's Cauchy. Try to make yourself a template and do this on your own. And assuming that you've had a chance to pause and try this, let's do this together. Let Sn be a convergent sequence. Suppose Sn is a convergent sequence. Say Sn converges to the value of S, so that we have a limit. Now we want to show that it gets really, really, really close to each other for some n and m when they're kind of close to S. So let's put an estimate on Sn minus m. So notice Sn minus Sm, I have to bound this somehow. So notice that this is definitely going to be equal to Sn minus S plus S minus Sm. Right? And these right here are saying that Sn is getting close to S. And these ones right here are saying SMs are getting close to S. Right? So by the triangle inequality, we know that this can be made less than, or that this is bounded by Sn minus S plus Sm minus S. Right? So this might give us an idea. We can control this. We can make it as small as we want. So let's try to make it less than an epsilon over 2. And we can control this to make it as small as we want. So we can make this be less than an epsilon over 2. And that could give us our bound to make the epsilon. Let's try this one out in green now. So start a proof of a convergence. Let epsilon greater than 0 be given. And our G cap again, so we've got epsilon greater than 0 be given. We can choose, let's choose capital N, what happens? Such that if, now n and m would be confusing here, so let's introduce a third variable for a subscript, such that if k is bigger than or equal to capital N, what do we want to happen? We want to choose the n such that if k is bigger than or equal to capital N, we have that sk minus s can be controlled to be less than epsilon over 2. That's our goal there, to make it less than epsilon over 2. And we can do this because the SNs did converge to S, even though we didn't know what S was. We do know that they converged to some number S. So now, if we take M and N being bigger than or equal to that capital N, we know that we have that Sn minus Sm can be made less than or equal to Sn minus S plus Sm minus S, as shown up here in star, and by our choice of capital N, this will be less than epsilon over 2 plus epsilon over 2, because both M and N come from bigger than capital N, and capital N was the bound for which beyond then everything was within epsilon over 2 of the S, and that's just equal to epsilon. That proves that Sn is Cauchy. So, So another argument where we're controlling our bounds, trying to make it less than epsilon, and we were able to do so. Okay, claim number 2. It turns out that every Cauchy sequence is bounded. Every Cauchy sequence is bounded. So let's see if we can show this one. Proof. We already proved a very, very similar theorem called that said that if we have a convergent sequence, that it was bounded. Remember, this was from a previous section, but because we didn't prove it in the previous section, I actually proved it in this particular slide, this particular video, set of slides. Just for punishment then, or just for practice, I guess, let's try to prove it again. So we're going to try to prove that every sequence, every Cauchy sequence is bounded. So let's approach that by saying, suppose, again, I should say, pause the video, see if you can try to mimic the proof, slide back earlier in the slides, take it down from Angel, and see if you can use that proof and modify it to work for Cauchy sequences instead of that convergent sequence before. But assuming that you've done that, assuming you've taken a shot and tried to do this on your own, suppose that Sn is a Cauchy sequence. So if it's Cauchy, we know something holds for every single epsilon that's positive. So let's let epsilon equal 1. Just because we can do it for any epsilon, so let's just let epsilon equal 1. So since Sn is Cauchy, we know that there exists a capital N in the natural numbers such that for all n and m that are bigger than or equal to capital N, we have Sn minus Sm can be made less than 1. And that's for all nm that are bigger than or equal to capital N. So, let's take Sm to be equal to Sn. In other words, let m equal capital N. What do we have now? Now we have for all n bigger than or equal to capital N, Sn minus S capital N is less than 1. So we found an actual term in the sequence, S capital N, that is bounded. Everything's really, really, really close to S capital N because of the Cauchiness. Okay, so by that previous homework, that previous exercise again way back in chapter 3, this would mean N, this guy right here, would definitely be less than S capital N, which is a fixed term of the sequence, plus 1. If you're getting really, really close to capital N, within 1 unit of capital N, then technically the SNs would be between S capital N plus 1 and capital SN minus 1, but at least they're going to be less than capital SN plus 1. Make it like that just to be safe. But again, it doesn't really matter too much. We can just keep that as just to be safe. So, we got our big M now. Can we find our max? Certainly. Let's let M equal of. Okay, remember we had all those junk terms at the beginning that can really screw things up for us if they wanted to. So let's let S1 be there, and S2 be there, and S3, and however many of these that we possibly need. But we'll stop off once we get up to S capital N. And then we'll just throw in this one extra term of S capital N plus 1, which we know was a bound for all of the SNs that were beyond N plus, and beyond that capital N, right? This inequality held for all of the N's that were beyond capital N. So, final conclusion, S little n is less than or equal to M for all N in the natural numbers. It's definitely less than or equal to the first capital N many terms, and then thanks to the Cauchy definition, we got an upper bound for the infinitude of numbers or terms of the sequence that are beyond that particular value. So that finishes the proof of every Cauchy sequence is bounded. Okay, last big theorem now then, the Cauchy convergence criterion. So I called this C cubed in case we need to refer to it in class. We will say that a sequence of real numbers is convergent. No, sorry, we'll not call this not definition. It turns out that a sequence of real numbers is convergent if and only if that sequence is Cauchy. The Cauchy is necessary and sufficient to show that sequence converges. Okay, ready? First of all, this is a biconditional, if and only if, but what did we prove in a previous slide? We showed that every convergent sequence is Cauchy. So, if it's convergent, then it's Cauchy. So the forward direction is what we call the lemma for C. Remember, I promised you we'd talk about this in a minute. There's our lemma for the big claim C3. We did our lemma, and so that means we can use that for the forward direction of C3. Okay, as before, general trick that we like to do sometimes is I'm going to let S equal the set of Sn in the natural numbers. So this is not viewing it as a sequence, as a big ordered n tuple again. This is just looking at the actual values or range of the particular sequence. And we're letting S be that particular set. Now, that set is going to fall into two different cases. Either that set is going to be finite, or it will be infinite. And so we'll look at those two cases separately and see how that shows us that the sequence must be convergent. Because now we're going to say that it's Cauchy, and we're going for convergence. Okay, let's start this off. So, suppose S is finite. Okay. Suppose S is finite. So, what do we know? Well, since Sn is Cauchy, Sn is Cauchy, exists a capital N in N such that Sn minus Sm less than epsilon, or all Nm that go beyond capital N. Right, that's our definition of being Cauchy. So, given Sm that is bigger than or equal to capital N, what can we say? Well, Sm and S capital N are both in S. Right? Sm was chosen bigger than or equal to capital N, and Sn, well, capital N is certainly bigger than or equal to capital N because it's there. And these are both in S because S was the set of all possible outputs, right? All the range of the particular sequence. So both of these things are definitely in S. If the distance between these 2 points, between these 2 points is less than epsilon, then the distance between them must be what? So if the distance between those 2 points must be less than epsilon, that means it must be 0. Right? Because what was epsilon? Oh, Nelly. Okay, bad Josh move here. I forgot to say where I got epsilon from, didn't I? Right? So it's true for any epsilon, but what epsilon am I using here? Well, if S is finite, then that means there's only a finite number of terms in there. I'm going to go back and do this in orange. At the beginning, I should have said where epsilon's coming from. We're going to let epsilon be the minimum distance between any 2 points. I should have written a storyboard before instead of going off the cuff here. So let epsilon be the minimum distance between any 2 points. We know that we can find this minimum distance. It's not going to be an inch. It's not going to be equal to 0 because S is finite. So we just take all of the little distances between any 2 points, and then we let epsilon be the minimum of those. So that's why down here now this conclusion is important, or this conclusion is now true, that if the distance between the 2 points is less than epsilon, which we know it is going to be, the distance between those 2 points has to be actually equal to 0, because epsilon was the least possible distance between any 2 points, and we just made sure to control this, so we made it be less than epsilon. Okay, so what does that mean? So this gives us the conclusion. Let's put this in another color. Let's put this in blue. So now the Sm, right, which is bigger than or equal to capital N, is actually going to be equal to S capital N for all m that go beyond capital N, because the distance between all of these points is less than epsilon, and epsilon was the minimum distance between any 2 points. So all the terms from some point on in the sequence must all be identical. And if they are all identical, then that means that Sn will converge to S. Right, Sn converges to S. I don't think I defined an S earlier too. Well, they're all getting really, really close to each other, so it's okay to just say that it converges. We don't need to tell what it converges to. And Sn converges. So that completes the first case where S happens to be finite. Okay. Now let's do the case where S is infinite. So now we have infinite, so we can't use that nice simple infinite or the argument about the minimum distance, because with infinitely many points, maybe the points have a distance of 1 over n from each other, right? And if they're all like 1 over n from each other, then that means the points could be half a unit apart, and then a third of a unit apart, and then a fourth of a unit apart, and so on and so forth. And so in limit, they would end up becoming infinitesimally close to each other. So the argument from before that epsilon could possibly be 0 if these points were too close to each other. So this is not going to work. So let's go with this now. So we're going to suppose that S is actually infinite. S is infinite, we did show that every Cauchy sequence is bounded. So at least we know that. At least we know that Sn is bounded. Right? Remember, that was one of those other. There's the big claim, and then the slide before the big claim. We showed that every Cauchy sequence is definitely bounded. So we certainly have that on our side. Okay, so we got the SNs are bounded. Now, from Bolzano-Weierstrass, by Bolzano-Weierstrass, this was the theorem in that section back on compactness that came after the topology section. We saw that there must be an accumulation point of S. So by Bolzano, we have a bounded set that's infinite. So S is infinite and it's bounded. So by Bolzano-Weierstrass, there is an accumulation point. There's an accumulation point S in S. So we definitely get an accumulation point here. We're going to try to show that that accumulation point is the limit of the sequence. So if you can get, we want to try to find some the elements of the sequence marching towards that accumulation point. So we will show accumulation point S is the limit of Sn, because that will give us the boundedness. We will then get the boundedness. So how do we prove something is a limit? We put on our G cap. So let epsilon greater than 0 be given. Yay! After epsilon is given, we have to find a capital N as a state condition. And that capital N for us is going to be given by the Cauchy, since we know that it was a Cauchy sequence. So since Sn is Cauchy, let N be such that for all N M bigger than capital N, we have Sn minus Sm is less than epsilon. Right, that was the Cauchy definition. Okay. Now we're going to use the fact that S was an accumulation point. So let's change the color up again. Since S is an accumulation point, what does that tell us? Well, that means that, remember, the accumulation point definition was that the neighborhood around it, I can't remember exactly how I defined it, but essentially there's got to be at least one point in the deleted neighborhood. There was at least one point in the deleted neighborhood, which meant that there was at least one point other than the point of itself inside of the standard neighborhood. So, since S is an accumulation point of S, let's look at the following neighborhood. Since S is an accumulation point, the neighborhood S neighborhood around the point S that had a radius of epsilon over 2 must have infinitely many points inside it. Infinitely many points of S. The accumulation point, now I recall, that was a couple weeks ago, but we defined it, our textbook defined it as having one additional point in the deleted neighborhood, but then you had a homework problem that had us show that there were infinitely many points inside of that neighborhood, inside of the true neighborhood. Okay, so if we're inside of this neighborhood, then that means what in particular? Here is an M bigger than or equal to capital N with Sm being inside of this neighborhood. Because remember, there's infinitely many points. So there's only finitely many that aren't there. So M, there has to be an M beyond capital N that eventually lands within that little monster neighborhood. So, what do we know from there? So, for N, for any N bigger than or equal to capital N, we have Sn minus S to Sn minus Sm plus Sm minus S is less than or equal to Sn minus Sm plus Sm minus S. And now this is going to be controlled to be less than epsilon over 2. So I guess I got to get back up here. Actually, I noticed that this puts an error. Yeah. Yay! There we go. So we can do that for any epsilon, so we just make sure it's less than epsilon over 2. And then we have the Sm that was inside of the epsilon over 2 neighborhood, so that's less than epsilon over 2 away from S. And that's just equal to epsilon. So therefore, Sn goes towards S, and hence it's convergent. That's the Cauchy criterion. So that's the end. Let's use an interesting application of this fact. So you might actually recall from a standard sequence and series course, that the sequence given by Sn equals 1 plus 1 half plus dot 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 plus 1 over n is divergent. I guess this would be more appropriately not called the harmonic series, but the sequence of partial sums of the harmonic series. And let's just show really quickly that this is actually going to be divergent. Okay, so look at proof here. If we happen to know that m is bigger than n, I think we need to be actually bigger than n. If m is bigger than n, then what do we get? Sm minus Sn is equal to, well, Sm is all of the terms up to 1 over m, and then Sn is all the terms up to 1 over n. So if we subtract those two from each other, we're going to have 1 over the first one beyond n, which is n plus 1, 1 over n plus 2, 1 over dot 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 dot, and this will continue up until we hit 1 over m. Well, this is bigger than, since m is the largest of all of these, then if I replace these all with m plus 1 over m plus dot 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 plus 1 over m, I'm definitely making this smaller because I made each one of the denominators be bigger, and making a denominator bigger makes a fraction smaller. I guess not every one. The last one stayed as an m, but all the other ones were given bigger denominators, and thus they have smaller value. But what's that equal to? Well, remember that this is m bigger than n, Sm minus Sn. So there's m minus n many of these, right? There's m minus n many of these. That means when you add them all up, you end up getting m minus n over m, and by the distributive property of division, or let's see, division through subtraction, that's 1 minus n over m. That might not look bad on the surface, but what happens? M, if we make sure that we choose m to be equal to double n, right? We just make sure that we go m going out twice as far as what n was. We end up getting, we get that Sm minus Sn is actually going to be equal to 1 minus n over 2n, or 1 minus 1 half, and that's equal to 1 half. You always get that Sm minus Sn is always going to be equal to 1 half. So, oh no, not equal to, sorry, bigger than, right? Notice it's bigger than. So that's not, this is equal, but this ends up becoming bigger than. erase this with inconsistent, bigger than 1 minus n over 2n, bigger than 1/2, that means that it is not Cauchy. So Sn is not Cauchy. Right? Being Cauchy means you could be, the Sn minus Sn has to be made infinitesimally small, less than epsilon for any epsilon. But this always has a bound of 1/2 on it. We can control it to always be larger than 1/2 as long as we throw in enough terms. So Sn, the harmonic series in the infinite case, right? This does not converge. Sn does not converge. Very good. Disappointing. We wish the harmonic series converges, but it doesn't. So that's the end of the proof. Okay, for homework, try problems 1, 2, 4, 7, and 14. And ideally, on Tuesday in class, maybe then we can start to try to do some of these problems or review our homework that was from section 4.2 and maybe even 4.1 problems. Maybe have some work with that. Okay, best of luck.